Hello everyone, this is going to be part 3 in the series of tutorials on C++ templates, and today we're going to talk a bit about template type deduction. So we're going to start off with 3 very similar functions, template functions to be specific. So we're going to make 3 variations of this foo. We'll have one that takes a t, one that takes a t reference, and one that takes a t pointer. So you can call foo and give it 42. You can make an integer x, and we would like to call foo with this x. And then finally, we'd like to call it with a pointer to an x. And right away we can see that this one doesn't work. So we'll start first by just commenting this out, and we like to see which of these ones we're actually getting. So if you run this, you see the first one we get is the top one. That's with this foo42. And the next one we get is with the t pointer, which is when we're taking the address of x, which gives us a pointer to that x. So the first question is, well, why doesn't this one work? And when you look at it, it says there's more than one instance of an overloaded function that would work with the way that we are calling this function. And it points out that it could be either the first foo here or the second one. And if you sit and think about it for a moment, you can sort of understand why that's correct. So we have this x, and the question is, do we want to have x passed around as a copy, or do we want to pass it as a reference? And you ask yourself, well, why didn't we have this problem with these other calls to foo? And with this call to foo, it's not ambiguous, because we know that this is going to be an int pointer, right? So this is the signature that matches most closely. With this foo, with this 42, this is an R value, right? So it's something that's temporary. And you cannot take a temporary by reference unless it's by constant reference. So here it's not ambiguous because it's not a pointer. You can't take it by reference, but you can take it just by copy. And what you can do that's interesting is if you add const here, now this one doesn't work, right? Because now it's ambiguous as well, because we could take either this 42 by copy, or we could take it by const reference. So here we're just trying to show a little bit how the type deduction can become a little confusing at times, but to explain why in certain cases there's an ambiguity. So what's also interesting to note is that if you removed this template that takes this t pointer, and we'll remove this one here, and we'll remove this one which doesn't compile. So we notice right away that this foo here that takes a t pointer still works. And you want to ask, well, which of the two is it actually calling? Right? So you can run it, and when we actually run it, yep, it comes to this one. And what happened here is that the template will add the pointer as part of the deduced type, right? So we say you have some type t, but it doesn't specify that t is just int or an int reference. The template is allowed to kind of add on a little bit to make it so that it matches the type. So in this case, this t is actually a pointer, right? So you can see the address of it, and it's pointing to the value 42. In a similar way, let's say you only had one that takes by reference, and you had this constant integer, and you want to call it with x here. So you can't have a reference to a constant integer, because this would allow you to mutate this x, which we're not supposed to be able to do. But you are allowed to have a const reference to x. So in the same way that when we had only a template with a t without the pointer, the template could add on the pointer to make it work. And in the same way here, even though we say our template only takes a tref as the argument, it's actually going to add on the const for you and make it work, because it'll try to deduce a type that works for what you give it, right? So just to show that we actually get here. So we actually get here, a better way to show that it's actually constant, actually would be more interesting. So I'm saying here that this t is equal to int const. So that means when you get here, this little t actually becomes int const ref, right? Because we have this additional ref. So if t was int const, we could do something like, okay, well, I'll have a t inside the function, and I'll make it 43, and then I'll try to do plus plus x here to increase it. But if we try to compile this, it doesn't actually work. And we can't do that because this t, right, like we said above, this t is a constant, so it doesn't work. But here, if I remove this constant, now it works, because t, the type of t is just int, and this little t becomes int reference. So we can make this big T an integer inside of this class, inside of this, not class, inside of this function. So it's just to show that the type deduction can add on little bits that are necessary. So there's pros and cons for this. So, or there's different uses, I should say. On one side, maybe all you want is to have T, and you can let the compiler kind of choose, okay, should I make it just a T, or should I make it a T pointer? And on the same side, you could say, well, I want it to be T reference. And the compiler could say, okay, well, should it be just T reference or should it be T const reference? And then you can do things like write your own const. So in this case here, I can pass this foo, this x here, I should say this const x, and now this t is going to be just int, but this will be an int const ref. Because here I specify I want to add const reference onto whatever the type of t is. So the only thing that's missing to make this work, because this needs to be a constant reference that we're passing, but since I already specified the const reference part, this t is just going to be int, right? Whereas if I remove this const here, then this template is going to make this int const. So the next thing we can look at is the ability to tell the compiler that we want a certain version of a template. So let's say we have something like, it could just be equals. And it'll take two types and return if they're the same, and it's templated. And what you can do is you can call this with two different types. And the problem here is it can't determine whether t should be an integer, as the first parameter is, or a float, as the second parameter is. And there's a few things you could do. So the first one is you could kind of say, well, this actually works on two different types just fine. But if you don't want to do that, and you probably don't in this particular case, what you can do is you can say, well, this float is actually just an integer. And in this case, it works. And this is the slightly better choice compared to doing something like this, which says this equals, for this equals, the t here should be integer. So I'm going to force all the arguments to be integers. And this is not as good as this previous line because it's removing the ability for the compiler to deduce the type. So here the compiler can see, okay, well this one is an integer and this one is an integer, so I'll say that the t is an integer. Whereas here you're telling the compiler, I don't care what types you see in the arguments, I want you to treat this as integers. And most of the time you're not going to run into any problems, but sometimes you may encounter scenarios where forcing them all to behave as a certain type is not safe. But those scenarios are rather rare. But still, you should always prefer not to force the compiler's hand. And we'll see a nicer example of why you want to let the compiler decide. So let's say we want to write some function called contains. And contains takes a pair of iterators, and it wants to determine whether there's a certain value in that range of iterators. So it's going to need some sort of a predicate. So the signature for a predicate is something that takes an argument of a certain type and then returns a bool. So we're going to start off by having this take a function pointer for the predicate, right? So for those who are not so familiar with the syntax of a function pointer, I'll explain it in just a moment once I finish writing this, and I'll explain what I'm doing here with this value type. Yes. And then we do for first not equal to last plus plus first if pred with first return true. Also we return false. Okay, so just to explain this is the signature for a function pointer. Right, so this is the name of the function pointer. So here it's predicate. In the same way that the name of this iterator is last. Right, so this is a function pointer called predicate, and that's how we use it. This is the return type of the function pointer, and this is the argument type. Now, the argument type of this predicate is something that we can determine from the iterator. And we're actually going to have to put type name here because this name's a type. So this is a dependent name, right? So inside of an iterator, it has a type def called value type, and that's the type of value that this iterator is pointing to, right? So if you have a vector of integers, the iterator has a type def inside it, says the value type of the thing that I'm pointing to is an integer. And because this type def inside the template may or may not be a type, we have to say specifically that this is going to be a type. You have to tell the compiler, by the way, this value type that's inside of this iterator template, this iterator type, is a type name. So we'll include vector, so we have something we can check what this contains. So we'll have this vector of ints, and it'll contain a few values. And let's say we want to make our predicate now. So we'll call it has a 2. And this takes a integer const ref I, and it just returns if I is equal to 2. Right? So given some integer, it'll return true if it's 2. So what we'd like to do then is we'd like to call contains with our v, and with this has a 2 as our predicate. So the first problem here is that, well, this doesn't actually compile. Oh, does it? No, it does not. The red line went away. It's tricky. So the problem is that the signature of this predicate doesn't match our actual predicate. And the difference is here this takes an int const ref, and this is just taking an int ref, right? So the const is missing. And that's kind of unfortunate because if something, you're always allowed to make something more strict, right? So if you have a function that, if you have an integer right? And a function wants an integer constant. You're certainly allowed to use your integer as an integer constant, because if you had an integer, you were allowed to mutate it. So if you want to give it to somebody who says, well, I'm not even going to mutate it, it's always safe to become more strict, right? You're giving them less liberality to change things. If you had a constant integer and a function says, hey, I want to mutate this integer, then it doesn't work because it's becoming less strict. So in this scenario, I would expect this to work with that, with this as this predicate, but it actually doesn't. So in this particular case, I have to add this const here. And now it happily compiles. So that's kind of one problem we had. So let's think of another type of problem. So what if we want to use contains not with a function pointer, but a lambda function, right? So we could have a lambda function that looks almost identical. It'll take int const I, and it just returns if I is equal to 2. If you try and compile this, it actually works too. And this is a bit tricky because a lambda function can actually be implicitly converted into a function pointer. So that's something kind of special about it. But what if we wanted to use a functor instead of a function pointer or a lambda function, right? So if we had some struct s and we wanted to use this as a predicate. And you can try and put this in here. But the problem is this one doesn't quite fit. And you say, well, why doesn't this fit? Well, this is a function pointer, which is exactly what we were asking for. And this lambda function is a bit special because it can be converted into a function pointer implicitly. But this can't really be a function pointer. And the reason why is this structure S is an object, right? So this function call operator inside of our structure S is not a function pointer, it's a member function. So you could use it in a case where you can provide a member function pointer, which has an even more bizarre syntax than this, which we're not going to get into. But it doesn't match this particular type of signature. So we ran into two problems here. So the first problem was that we couldn't use a function that was compatible with this signature, right? So if it was not const here, this function signature should still be compatible with what we need because it's more strict. The second problem was that that very particular function signature doesn't allow us to use structures. So the question is, well, what could we do instead? Because we know we need some sort of predicate that's going to act on whatever the type of the integer is and is going to give us a bool. And the answer is to just let the compiler use type deduction and figure it out for itself. So what you can actually do here is you can just write, well, I want some other type, and I want the type to be my predicate. And then the question is, well, what do we change the signature to? And it's actually very simple. And that's it. First of all, it's much easier to read. And this pred can now be anything, right? Because the compiler will decide what type to deduce to put here. So one thing that's nice is that we can now have I need to be more specific. Okay, let's start with just this first. Because how would I disambiguate them? Okay, well, I won't write two separate ones, but it compiles, first of all, right now. So the first thing that we gained is we can use this structure, right? So we see that now. And the second thing is, if I remove this const, it still works. So I can use a function whose signature kind of matched what I originally had, but I could also use something more strict. And if it doesn't work, the compiler will simply tell me, well, whatever this pred type is that you're trying to use like a function doesn't work. And this ties into the idea of concepts that was mentioned in the second part of these tutorials. And here, predicate is a type that shares the concept of being callable, right? So a function is callable, a lambda function is callable, and a functor is callable because it has this function call operator. So anything that is callable and has a compatible signature, right, for the arguments we're trying to give it, will work. At the same time, it makes sure that you're safe. So here, for example, if I put cBegin and cEnd, right, so now I'm not allowed to change the items that I'm pointing to. So this one works fine because has_a_to takes things by const or int const ref. But if I remove this const now, oops, it doesn't work. So first of all, let me just count these up to ensure that it's this one. Here it says I can't convert between the types because I am losing qualifiers, right? I'm losing the constness of my types. So the compiler will still make sure that everything is safe. So just to give a quick little reference table about these template type deductions. If you have an int x, a const int y, and what are we going to do? We're going to have a int reference z looking at x, and an int const ref. What am I going to do after z? I guess I'm going back around to a. Looking at y. Okay, so here we have the different combinations of constness and reference, right? So we have an int that is neither a reference nor const. We have an int that is const. We have an int ref pointing to an int, or referring to an int. And we have a int const ref referring to an int const. So auto behaves in very much the same way as template type deduction. The only exception is that it behaves a bit differently with initializer lists, but I think they're actually changing that in C++ 17 so that it becomes more regular, but I'd have to double check on that. So if we want to try having this refer to different types, just to see what it is that we're getting with each one, and I went around to A. Okay, so we're again going to have all the different combinations of constness and reference, all of these. Oops. Other way around. This is 7. This is 6. This is 8. 9. Whoops. 10. 11. 12. So here the type is simply going to be int. Here the type is also going to be int. And it's not, so why was it int const? Well, we're making a copy of it. So the minimal acceptable type is an int because we're not referring to this y, right? We're going to make a new one. Here with z, this will be also an int. And again, we're just going to make a copy. We're going to ignore the fact that this was a reference. We're just making a copy. It's the same way like when you use auto in a range base 4 that you have to remember to add your own reference even when you're referring to something that exists elsewhere. Otherwise, it's just going to make a copy. And same thing here. Because we're not specifying that this needs to be a reference, these are all just going to be integers, and they're all going to be non-constant. So now we have references. So this will be an integer reference that's referring to this x. This one is referring to an int const. So it needs to add the const in order for it to be safe, right? So here we have the const was added. here we are referring to z. So here we'll just have an int ref. And here we're referring to an int const ref. So we will have an int const ref. And for this last part, these are all going to be int const ref because we kind of forced the compiler to go that far. Right, we said that, well, whatever type you deduce for auto here, you're going to have to put const ref onto the end of it. So the most interesting things to note is that you don't need to specify the const yourself. I mean, obviously, if you want to treat it as a const, you can add the const. But in cases where the const is absolutely required, it will be added for you, right? And this is more relevant for templates, because in templates, you might want to deal with constant and non-constant types, right? So rather than saying, well, it absolutely has to be constant, you can just say, well, if I take some sort of reference and what you give me is a constant, then the compiler will say, okay, well, I'm actually going to say that my t is a constant t, and then it'll become a reference to a constant t. Right? So the point is just, it's best to let the compiler do the type deduction for you, and you should only add on things when they are absolutely required or when you want to give them special treatment. So again, for special treatment, it was the example with, do I want a t or do I want a t pointer? If you say a t pointer, then when you use the template, it will only match pointers. Whereas if you say I want just a t, and it can be any t, if your t is not a pointer, it'll be just a regular t. If your t is a pointer, it will be a pointer to t, right? So that's again with these type name, no, other way around. Template, type name t, void foo. If you try and pass a t pointer into this foo, then this t will become whatever your type is, a t pointer. So let's say use an int, for example. If you pass an int pointer in here, then this will become an int pointer automatically without you having to do something. And that's it for now. Thanks for watching.